Hello friends. So in this lecture we will discuss the definition of normal subgroup and some examples of normal subgroup and some theorems related to the normal subgroup. So let us start with today's lecture with definition of normal subgroup. So the definition of normal subgroup is the definition of normal subgroup is let capital G be a group and capital H be a subgroup of G. Capital H is said to be a normal subgroup of G if X H X inverse is subset of capital H for all X belongs to G. In other words, this can be written as or for X belongs to G and small h belongs to capital H, X H X inverse belongs to capital H. So in order to show that any group is a normal subgroup, it must be a subgroup. Then additionally, if this condition gets satisfies, then we say that H is a normal subgroup of G. Now, examples of normal subgroup. First example, let G be a group with identity element E. Let capital G be a group with identity element E, then G and singleton E are always normal subgroups of G. G and singleton E are always normal subgroups of G. How? Solution. Claim singleton E is normal subgroup of G. For that, let X belongs to G and H belongs to H. Here capital H is nothing but singleton E. So H is nothing but E identity element. Then X H X inverse is equal to X E X inverse is equal to X into X inverse. So X and X inverse cancel out each other and we get identity element which is belongs to singleton E. So for all X belongs to G and H is equal to E belongs to singleton E, X H X inverse belongs to singleton E. This implies that singleton E is a normal subgroup of G. Is a normal subgroup of G. Similarly, we can show that G is also a normal is also a normal subgroup of G. Next example, let G be an abelian group. Let G be an abelian group. Let G be an abelian group. Then prove that every subgroup capital H of G is a normal. Then prove that every subgroup H of G is a normal subgroup of G. Solution: let capital H be any subgroup of G where capital G is an abelian group given. This is given. So this implies that capital H is also a abelian group. Therefore, uh, let X belongs to G be any arbitrary element and H belongs to capital H, which is subgroup of G, implies H is also belongs to G, and X inverse is equal to, as X belongs to G and H belongs to G and G is a normal subgroup, we have Hx into X inverse is equal to H belongs to capital H. This implies that X inverse belongs to capital H for all X belongs to G and for all H belongs to capital H, implies that every subgroup of a normal group of an abelian group is normal. Every subgroup of an abelian group is normal. Next example, third one, let capital G be a group. Let capital G be a group and Z of G is equal to X belongs to G such that XA is equal to AX for all A belongs to G. This is called centralizer or center of a group is an normal subgroup of G, is n normal subgroup of G. So by applying the definition of normal subgroup, you can easily prove that this is also a normal subgroup of G. So there are many more examples which will be given in the notes provided to you in your WhatsApp group. So let us discuss an important properties of a normal subgroup. So the first theorem so we are going to discuss is related to the definition of a normal subgroup, and that theorem states that the necessary and sufficient condition for the normal subgroup. Okay, so let us see what is the statement of that theorem. Let capital G be a group let capital G be a group and capital H be a subgroup of G, then following statements are equivalent. Then following statements are equivalent. So first one, capital H is a normal subgroup of G. Second one, XH X inverse is equal to capital H for each X belongs to G, or each X belongs to G. Third one, XH is equal to HX for all X belongs to G. That is every left coset of capital H in G is a right coset of capital H in G. Okay, so these three statements are equivalent. That is, first one implies second one implies third one, and third one implies first one, and so and we know that equivalence relation is an transitivity, so each and every statement implies and implied one another. So let us see what is the proof and how we will prove that. So assume the first statement, or we will prove first implies second. Suppose capital H is a normal subgroup of G. Suppose capital H is a normal subgroup of G. Therefore, by definition of normal subgroup, we have what is the definition of normal subgroup? The definition of normal subgroup is XH X inverse is subset of capital H for all X belongs to G. Suppose equation number 1. Now if X belongs to G, this implies that X inverse also belongs to G, because G is a group. So every element has its inverse in G. Also note that for any two subsets, capital A and capital B of G, if A is subset of B, then X into A is also subset of X into B, and A into Y is subset of B into Y for all X, Y belongs to C. So this keep in mind. So we will get the proof of our result. How? From equation number 1, we have XH X inverse is subset of H, implies that X inverse X H into X inverse is subset of is subset of x inverse of h, which implies that, so this x inverse into x is nothing but identity into x, x inverse is subset of x inverse of h. So using this we get using previous estimation we get, that is, what is the previous estimation? We had assumed that, what, equation number 1, what is the equation number 1? X inverse hx is subset of capital H. This implies that x into x inverse hx into x inverse is subset of xh x inverse. This implies that using the associative law of cosets, x into x inverse is subset of xh x inverse, which implies that EHE is subset of XH x inverse. This implies that H is subset of XH x inverse. Suppose this is an equation number 2. Now from equation 1 and 2 we get H is equal to XH x inverse for all x belongs to G, which is nothing but our second number statement. Similarly, we will prove that first implies third. To prove that statement first implies statement third. Suppose for every x belongs to G, suppose for every x belongs to G, XH x inverse is equal to capital H, sorry, here we are proving that second implies third. Suppose for every x belongs to G, XH x inverse is equal to capital H, which implies that x h x inverse into x is equal to h into x, what, post multiplying by x, which implies that x h x inverse into x is equal to h into x, which implies that so this x inverse into x is nothing but identity is equal to x, so xh is equal to hx, that is every left coset of capital H in G is a right coset of capital H in G, capital H in G. Now we will prove that the statement third implies statement first. Now to prove that third implies first, so what is the third statement? Third statement is that for all x belongs to G, xh is equal to hx. To prove that, what we have to prove? To prove that h is a normal subgroup of G. To prove that H is a normal subgroup of G. So in order to prove the normal subgroup, we have to use the definition. So we have what we have given, xh is equal to hx for all x belongs to G. So this implies that x inverse xh is equal to x inverse hx. This implies x inverse into x. This is what? Pre-multiplying by x inverse. Pre-multiplying by x inverse is equal to x inverse hx. So this x inverse into x is nothing but identity into h is equal to x inverse hx, which is equal to h, that is x inverse hx is subset of h. Hence by definition of normal subgroup, H is a normal subgroup of G, hence the proof. So next theorem, what is that? If H is a subgroup, of index 2 in G, then H is normal subgroup of G. Then H is normal subgroup of G. So what is mean by the index? Index is nothing but the number of left cosets or the number of right cosets. So in order to find the index in finite ordered groups, simply we are dividing the order of group by the order of that subgroup. But in infinite ordered group, the index is nothing but actual the counting of the number of left cosets or the number of right cosets. So the proof is very simple. We know that the index of H in G is denoted by this notation, square bracket G has to H is the number of distinct left or right cosets of capital H in G. Also, we know that EH is equal to H is always a coset. Now let small a belongs to capital G such that A does not belongs to capital H. This implies AH is not equal to H. So this implies that AH is left coset. And G has only two cosets. This implies G is equal to H union H. Similarly, HA is right coset. This implies that G is equal to H union HA. H union HA. That is, here we obtain two equations. What are that? First one, G is equal to AH union H. G is equal to HA union H, and AH intersection H is empty. HA intersection H is empty, and AH union H is equal to HA union H. This implies that AH is equal to HA, isn't it? For all A belongs to G, this implies that every left coset is equal to right coset, and hence, using the previous theorem, we have H is normal subgroup of G. H is normal subgroup of G. That is, when the group has index 2, if any group has index 2 in G, then that group is normal subgroup in G.